Okay, the second great, actually the first great problem of calculus, which is the area under a curve. That was the first because the Babylonians actually kind of figured that out. So this was the first great problem of calculus. The second big idea was the other one, slope of tangent line. But so in the past, we've been able to determine the area of regions bounded by straight sides, such as rectangles, triangles, trapezoids, etc. How do we just determine the area of a region with curved sides? This is the first big idea of calculus. If y equals f of x is a positive function, that is, its graph lies above the x-axis, then the area under the curve, y equals f of x from a to b, where a is less than b, is defined to be the region below y equals f of x above the x-axis, so just in here, to the right of the vertical line x equals a, and to the left of the vertical line x equals b. How do we determine the area of this region? So the idea is that we can start off by approximating it, approximate the area by dividing it into vertical strips of equal width, as shown in the diagram above right, and approximating the area of each strip with a trapezoid. We'll be using trapezoids that have two adjacent right angles, as shown by the three views below. So we're looking at trapezoid in this orientation, right? So this is the height. These parallel sides are B1 and B2, or we call them A plus B, or A plus B 1/2, HA plus B. So here's our height, right? Here's B1 and B2, and then we're saying, well, look, if you look at these, in this case, it's really almost a straight line, and not quite, okay? How could we get a better approximation if we were going to do this? Like this idea.
Smaller strips.
Make smaller strips, right? So, what we're going to do is estimate the area under the curve y equals 3 root x plus 1 from x equals 2 to x equals 8 by dividing the region into three vertical strips of equal width and approximating the area using trapezoids. We're going to write our answer as a simplified exact value, and then for some reason we're going to round it to the nearest hundredth. I don't know why. I think we'll just plug it into our calculator and figure it out. Because really it's just, if we round them, then we've got approximations to approximations, right? I think it's just a holdover from the book, because there weren't calculators back then, much, sort of. Actually, maybe there were. But anyways, so let's start off by just drawing a little diagram of this. What does this look like? I mean, it's a square root curve, and it's going to start here and do this. So, there is y equals 3 root x plus 1. And we want to go from x equals 2. How big will the strips be if we're making 3 strips? 2 units, right? So 2, 4, 6, 8. And divide the region into 3 strips of equal width. Approximate the area using trapezoids. Okay. So first thing we should do is figure out, well, what's the width of our strips? I mean, we figured it out, but let's formalize that. So the width of a strip.
8 minus 2 divided by 3.
Yeah, it's 8 minus 2 divided by 3, right? So width of strip. So we're going from, if we think about it, just going more general, we're going from A to B, so it's B minus A, so it's the distance from B minus A, or from A to B, which is B minus A. So we'll call that delta x, and it'll be B minus A over the number of strips, okay, so let's say over n, do n strips. And for us, we can fill in the number, so it's 8 minus 2 over 3, which is 2. Okay, so that's our delta x. That's our change in x, right? We're going from 2 to 4, 4 to 6, 6 to 8. All right, and so the area. So if we look at the area, then we need to know how high this is. So how high is this? Really? So what's an expression, right? We call this f of 2, right? So we'll need f of 2. And we'll need f of 4. And we'll need f of 6. And we'll need f of 8. Okay? So we need f of 2, f of 4. So using the formula for the area of a trapezoid, we're going to take, so let's say area. So area is equal to, so it's going to be f of 2, so that's b1, plus f of 4, that's b2, okay, divided by 2, this is the 1/2, right, it's 1/2, and then times the height, which is delta x. Plus, okay, so that's the first trapezoid here. So we'll call that, like, that's area number 1. Area number 2, well, we're going to go f of 4 plus f of 6. So that's b1 plus b2 divided by 2 times the height. Okay, which again, we're just saying delta x for now. That'll be area number 2. So this is area 1. This is area 2. And the third area is going to be, so the third area, b1, f of 6, plus b2, f of 8, over 2, right? The over 2 is because of the half in the formula, it's 1/2, b1 plus b2, and then h. And so that's area 3. All right, so we can simplify this a little bit, because what do all the terms have in common? They got a delta x, and they're all divided by 2. So we can factor that out, right? Delta x over 2. And we're left with f of 2 plus, well, okay, wait a sec. How many f of 4s do we have?
2.
2 of them, right? 2 f of 4. And what about f of 6? How many of those?
2.
There's 2 f of 6s, and what about f of 8?
3. 1.
Only one of those, right? It might be area 3. There's only one. Okay, and so now what we could do is just go in and substitute values, right? So we have expressions. Really, this is kind of a general thing. We could do this, now we're going to say, all right, for our specific example, delta x is 2, right? The height was 2, divided by 2. F of 2, well, that's going to be 3 root 2 plus 1. 3 root 2 plus 1. Plus 2 times f of 4. What's f of 4? So root 4, 2, 6, 7. Right? So 2 times 7. F of 6. So that's going to be 3 root 6 plus 1. So 2 times 3 root 6 plus 1. Plus f of 8. So root 8 is 2 root 2, 6 root 2 plus 1. So this will be 6 root 2 plus 1. All right, and now we can do, well, 2 and 2, 2 over 2, that's just 1, right? So we've got, let's just expand it. So we got 3 root 2 plus 1 plus 14 plus 6 root 6 plus 2 plus 6 root 2 plus 1. And collecting all our terms, so we've got 9 root 2's. 9 root 2's, and we've got 6 root 6's, and we've got 14, 15, 17, 18. Add that up right? Yeah, 18. Yeah, grab one. Okay. So now they gave us the approximations, right? So we need 9 times 1.41 and 6 times 2.45. 9 times 1.41 and 6 times 2.45. And I have previously done the math. 19.70. So it's going to be 12.69 plus 19.70 plus 18, which is 45.39. Okay, or we could just actually haul out our calculator. But it doesn't work anyways.
Wabbit emu?
Wabbit emu. Yeah, I know, eh? Like, is it a wabbit or is it an emu? Okay, what did we have? 9 root 2. Okay, I gotta clear that. So 9 root 2 plus 6 root 6. Okay, so closer, 45.42. Whatever, right?
What?
Okay.
What's 6 multiplied by 2?
All right. I mean, I was close. It was off by 0.03, the rounded value from the calculated value. To approximate the area under the positive function, so just in order to generalize this, right? We kind of did a bit of a general bit at first, but the area under the curve using trapezoids of equal height, we do the following. So we determine the height. So what's an expression we're going to use for the height, this being the height? Right, here's the height. Height.
So you want to say now about n or 6 factors.
So what do we use?
12, that's all. Yeah. 6 multiplied by 6 is not 19.
No?
6 times 3 is 8. 2.45.
Oh, maybe I reversed the numbers then.
We're doing the other question.
Oh, sorry, it's 14.70. Okay, still, it's going to add up to that. My bad, can't read the writing. Okay, the height. Well, the distance between divided by the number of strips we're going to split it into, right? So b minus a, how far apart are they, divided by n, and then so how big will each strip? Determine the approximate x values between a and b using. Okay, so let's call this x sub 0, and let's call this x1, x2, x3. Let's get down to here, we'll call this xn. This will be xn minus 1, and we'll call this dot, dot, dot. Right, so we're splitting it into n regions, right? That's what we're doing by dividing this. B minus a over n, we're finding out how wide each region, each of the n regions are. So between 0 and 1, this will be region 1. Between 1 and 2 is region 2. Between 2 and 3 is region 3. And this is region n minus 1. And this is region n, right? That would be the nth region. Okay, and we're going to figure out their areas. So determine the approximate x values between a and b using, so x0 is equal to a. So what's x1 equal to? A plus, what do we call it here? H, a plus h. And what's x2 equal to? A plus 2h. And what's x3 equal to? So then x sub n is equal to a plus nh.
Oh, no.
Right? So n h's. Determine an approximation to the area by using the formula. A equals, actually I want to kind of move that. So let's start here, because we'll do a few lines, right? Because we'll start off with a more complicated expression, we'll simplify it down. So, just as we did before, right? We'll say, well, it's going to be f of x0, so that's b1, plus b2, which is x1, over 2 times the height, so say times h, plus f of x1 plus f of x2 over 2 times h. Okay, so this is region 1, right? x0, f of x0 plus f of x1, so b1 plus b2 over 2 times h. Region 2, f of x1 plus f of x2 over 2 times h. Okay, and we'll keep going. So f of x2 plus f of x3 over 2 times h. And ending with f of x sub n minus 1 plus f of x sub n over 2 times h. There's an h there. And to simplify, we'll do what we did before, right? So we'll pull out the h over 2, right? H over 2 is a common factor. We'll extend the page. So area is h over 2. Okay, and then what have we got, right? So we've got f of x0 plus, okay, what about the x1? There's 2 of them, right? So 2f of x1. Because it's the right boundary of the first region and the left boundary of the second region. So plus 2 f of x1 plus 2 f of x2 plus 2 f of x3 plus dot 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 2 f of x sub n minus 1 plus f of xn, right? So that's the very right boundary, and that's only going to occur once, right? So the left bound only occurs once. It's the left of region A, and it doesn't repeat. This is the right boundary of region 1, but the left boundary of region 2. This is the right boundary of region n plus 1, but the left boundary of region n, and then the right boundary of region n, just that once. And so what we can say then is it's h over 2. So we could say it's f of a plus 2f of x1 plus 2f of x2 dot dot dot, and we'll get 2 of the f of x n minus 1 plus f of b. So that's a formula using a and b as the left boundary and the right boundary, and then x1 through x sub n minus 1. I think that's on your formula sheet. So it must be important.
It's on that one.
It's on my formula sheet. I can't find the formula sheet. Yeah, it's on your formula sheet. In that form, right? And it says where h is equal, so let's throw in the rest of it just because it's on your formula sheet, that's fine. So where h, so this is on your formula sheet, and then it just says where h is equal to b minus a over n, and x sub I is equal to a plus IH. Okay, so again, that's just what we did, right? We said x1 is a plus h, x2 is a plus 2h, so xi, x10 is a plus 10h, and so on. Okay, and then we can use this formula. So approximate the area under the curve y equals sine x from x equals 0 to x equals pi using 6 trapezoids. Write the answer as a simplified exact value. Okay, so let's take a look at sine x from 0 to pi. So if I'm using 6 trapezoids, well, really, that's about all we need. I don't necessarily need to draw in all the trapezoids and stuff, right? So what do we say? Well, we say, okay, so h is equal to b minus a over n. So what's b? And what's a?
0.
And what's n?
6.
So h is pi by 6. Okay, so we got a formula, right? I'm not going to write the formula out, but we'll just substitute it into the formula. So a is equal to 1/2 h. So 1/2 times pi over 6 times f of a. So f of 0 plus 2 times f of, okay, what's next? Pi over 6. Yeah, plus 2 pi over 6. Plus 2 f of
2 pi over 6
or pi over 3. Plus 2 f of
1 pi over 2.
yeah, 3 pi over 6 or pi over 2. Plus 2 f of, I'm going to start writing smaller. Okay, so we've got 0 pi over 6, 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 2 pi over 3, plus 2 f of 5 pi over 6 plus f of pi. Okay, so that's just using the formula, right? So on your formula sheet, we're just substituting in. Going from 0 to pi by pi over 6. And now, I'll start at the left edge where I should have started. So we've got pi over 12. So we can work all these out. Well, f of 0 is just 0, right? We've got 2 times f of pi over 6, sine of pi over 6, a half, right? Plus 2 times sine of pi over 3, root 3 over 2, plus 2 times sine of pi, pi over 2, plus 2 times, then we just go backwards, right? I mean, we just kind of working our way around, or up, around the unit circle, which goes that way. So 2 times root 3 over 2, plus 2 times a half, plus 0.
Wait a second.
So pi over 12, just going through and simplifying this, we've got 0 plus 1 plus root 3 plus 2 plus root 3 plus 1 plus 0. And what have we got? So we got 2 root 3s and we've got 4. 2 root 3 plus 4, which is divisible by 2. So it would be pi over 6 and root 3 plus 2. Which is about 1.954. I just worked that out because, well. And the actual area is 2. But we'll get to that, right? So there's a way we can figure this out without, but this is the start of it, right? Like we just jumped in and said, hey, here's how you do this. Like, where'd that come from? It came from this idea. Oh, wait, edit, delete page. Next, properties of sigma notation. So we're going to be adding stuff up, right? If we're going to be adding stuff up, then we're going to use sigma notation to add stuff up, right? So we need to go through some properties of sigma notation, which will help us when we add stuff up. Remember from Math 30-1 in the beginning of this course that the sum of I equals 1 to n of t sub I is equal to, so we got t1, okay, so it's the sum of n terms. Properties of sigma notation. All right, so what if I'm adding up c? Just c, I equals 1 to n of c. What is that? C plus C plus C plus...
Infinity.
Well, but how many of them are... No, it's not infinite. It's how many of them are there?
Oh. NC.
NC. I want to follow that up with an I somehow. NC, I see that... No. Okay, so it's NC, right? So if you're adding up a constant however many times, then it's just the however many times the constant, right? Okay, what if we have C times T sub I? So it'll be CT1 plus CT2 plus CT3. So what's it going to be? So we can factor a C out of each term, right?
Yeah.
Okay. So if we do that, let's see if we can squish that in here. So it's C times T1 plus T2 plus, which is equal to C times, what's another way of saying this? Just the sum of I equals 1 to n of t sub I. So if there's a constant that's being multiplied by whatever it is that you're doing the sum of, the t sub I, the terms, you can just pull the constant out front, right? And multiply it by the ultimate sum. Okay, so property 1, if you're just adding up a constant, it's just n times however many times you're doing it, times c. And what if you've got two separate terms, ti and si? So it'd be t1 plus or minus s1 plus t2 plus or minus s2 plus t3 plus or minus s3, ending with t sub n. So what's another way we could just express that?
It's already written out.
Yeah, but you can kind of simplify it a bit. So say the sum of things would just be the individual sum. Or we could just add up all of the t sub i's and then add to that the sum of the s sub i's.
Oh,
Okay.
oh, okay.
Right? So we could just say, well, then you could just take the sum
Let's see, I plus it.
plus or minus
Is that sigma? Sigma, right?
Okay, so sort of the sum of terms is also the sum of the individual sums. Right? We could just add them up separately and then add or subtract them one from the other. Okay. I think it's become a little more clear when we do it with actual real things. All right, so we've got those three properties, which we shall now use. So special sums. What kind of sum is that? T1 plus I minus 1 times D. Recognize it?
Vaguely, but I don't remember what it means.
It's got something to do with arithmetic.
Something mathematical?
It's an arithmetic series. So we won't pronounce it arithmetic, we'll pronounce it arithmetic. I don't know why we do that. Okay, it's an arithmetic. Okay, probably we should have written the first few terms. Oh, see, you got ahead. You may want to write the first few terms. Okay, so what are the first few terms, right? It would be T1 plus 0D plus T2 plus 1D plus, or sorry, T1 again, T1 plus D plus T1 plus 2D plus, and then the kickers would have given it away, T1 plus N minus 1 D, or at least it would have given it away if you'd been in Math 20 and said, oh, right, arithmetic series. General term of an arithmetic series. Or that's right, general term of an arithmetic sequence, and when you add them up, you get the arithmetic series. Write an expression for the nth partial sum. Okay, so all we're doing is writing down the formula for the sum of an arithmetic series, and we actually give this to you. It's on the formula sheet, so we're just going to write it down. Oh, hang on, sorry. No, what? I'm on the wrong page. Never mind, we don't give this to you because you're probably not going to need it, but. Okay, so S sub n, which is equal to the sum of I equals 1 to n of T1 plus I minus 1 times D. Okay, so we call that S sub n, is equal to n over 2 T1 plus Tn, or n over 2 2T1 plus n minus 1 times D. So sorry, that's the formula for an arithmetic, which we don't really do a lot of, but it's a special sum number 1, adding up an arithmetic series. So if that's an arithmetic series, then this is a, oh wait, we might want to write a few terms first. So this would be equal to T1 times r to the 0, or just T1, plus T1r, 2 minus 1 would be 1, plus T1r squared, plus T1r cubed, and so on, up to T1r to the n minus 1.
Geometric?
That's a geometric series. Geometric series. And a geometric series has a couple of formulas for it. And they are, so let's just do this. S sub n is equal to T1 times r to the n minus 1 over r minus 1, or r Tn minus T1 over r minus 1. Okay, so those are formulas for sums of arithmetic series and geometric series.
Can you go back to the arithmetic?
Yeah.
Mm-hmm.
Because like nobody
So these are the two formulas. They're not on your sheet. If you needed them, we'd give them to you, I think. I don't expect you to memorize those, right?
didn't we do this?
Yeah, you did that in 20-1. I don't know if you did you do any of this in 30-1?
I did last year.
Yeah, okay. So 20-1 and 30-1. It all builds. Okay, but now the important stuff. The one that actually we're going to be using, and the ones that we give you formulas for. So what does the series I equals 1 to n of I represent? So, well, it's going to be 1 plus 2 plus 3. So what is that if I add up 1 plus 2 plus 3 plus 4 plus?
What? The sum
And what kind of numbers are those? 1 plus 2 plus 3? Yeah, but it's a little more back to earth. A little more not artificial. It's natural. Well, yeah, okay, but we'll go with natural. Yeah, vote green. It's natural numbers. Although a Green Party candidate withdrew and said, vote NDP. I think he could be. So this is the sum of the first n natural numbers. Okay, so the sum of the first n natural numbers. Where did it go? Write an expression for the partial sum. Okay, so we give this to you, and it is. So let's just throw an equal sign down there, and it is n times n plus 1 over 2. Which is really, the natural numbers really are just an arithmetic sequence, right? Just where T1 is 1 and D is 1. So you could plug this into the formula for an arithmetic sequence and you would generate this formula, okay? So, special sum number 4. What is the series the sum of I equals 1 to n of I squared represents? The sum of the squares of the, yeah, so it's the sum of the first n squares, right, or whatever. So the sum of the first n, I don't suppose it needs that, squares.
It's just like you.
First n
It's a
natural
square.
squares or just first n squares?
Well, you could say it's the sum of the first n natural numbers, the sum of the squares of the first n natural numbers, but really, I would just say it's the sum of squares, okay? The sum of squares.
The squares are rectangles.
An expression for the sum of squares is this, which is given to you on your formula sheet. So it's n
Doesn't necessarily mean it's not a square though.
times n plus 1 times 2n plus 1 over 6. So if you find yourself in the capacity of having to add up the sum of the first n natural number squares, or the sum of the squares of the first n natural numbers, this is the formula you will use. And it's on your formula sheet. So if that's the sum of the squares, then what's this?
Cube.
It's cubes. Okay, so it's the sum of the cubes. Okay, of the first n natural numbers. Let's throw that in, first n natural numbers. And I'll go back and do the squares. Sum of the squares of the first n natural numbers. Might as well be specific or and the formula for the sum of the cubes is which formula you have?
N squared plus
N squared times n plus 1 squared
yes.
over 4.
It's
I don't even know where they got these, but they got them from somewhere. They're magic. Yeah, they are. It's like as if, like, that's why it's on your formula sheet. Probably Galileo when he was 8 did it. Let's see when it's 7. Okay, so examples for finding sums of finite series. So what if you have to add up a finite series? So we want the sum where I equals 1 to 10 of I cubed plus 5, right? All right, so hang on. We did something. We have some properties hanging around, right? We got some properties. And what did it say? Well, if you were summing up, doing a sum or a difference, then you could split this out and write it as the sum of I equals 1 to 10 of I cubed plus the sum of I equals 1 to 10 of 5. Right? So we use that property that if I'm summing up a sum, that I can just do the sum of the individual sums. I just can't say this. You see, the math says it for us. Okay, so we have a formula for this, right? And the formula for this is n squared. So n squared, this could be 10 squared, right? Times what? Was it n plus 1 squared? Over what? Over 4. Plus, and what's the sum of this?
50.
Yeah, 50, right? So 10 times 5, 50. I don't know how you want to write it out. There's little tricks we could do. Maybe, I don't know, plus. Well, let's just write it as 10 times 5, so we just recognize that. So what do we got? 100 times 121 over 4 times 50 plus, you're right, plus 50. I'm going off script. Actually, it's not even on my script. They changed the thing, they changed the question this morning. So. That's 25, right? Yeah. Okay. So we could do this. 25 and 121 plus 2. Right? Because I just factored 25 out because I'm doing this without a calculator. So 25 times 123. Did you use a calculator? You do what? Did you do it without a calculator? Yeah. Cool. What was it? 3075. Okay. We're not. I don't see us asking you. Maybe that's not really that hard. That's doable, right? Pencil and paper. Okay. The sum of n equals 1 to 20 of 2i minus 3 squared. What? Is it a different number?
I think 3065.
Oh my god, get our calculator.
25 by 1. 25 by 130.
Wait, we don't need no calculator. How many times does 4 go into 123?
I don't
Like
know.
30.
Never mind. Yeah, it's 75.
There, you don't. I know,
You
it's
can't
like.
get 60. You can't get 3065 multiplied by 20.
Yeah, that's true. You can't get a 65. It has to be a 25, a 50, a 75, or 2 zeros.
Come on, Jared. What were you thinking? It was me. I'll help you. You're letting down the team.
Well, he may have doubted you. Okay, what are we going to do with this? Because we don't have a thing that says, so we had a thing that says, hey, I can split this up, but this is squared.
We have the I squared thingy.
We do, but here's what we should do. Let's try this. The sum of I equals 1 to 20 of, how about 4i squared minus 6i plus 9? Huh? So because the quantity in parentheses was squared, we're going to have to square it. All right, cool. So we'll square it. Now I can split that up into a sum or difference of sums. That's sum or difference.
Oh.
So the sum of I equals 1 to 20 of 4i squared minus the sum of I equals 1 to 20 of 6i plus the sum of I equals 1 to 20 of 9. Furthering this, we can then say, well, I don't really want to do 4i squared. Let's pull the 4 out front, right? Because we know that a constant times a term, right? The sum of constant times a term is the constant times the sum. So it's 4 times the sum of I equals 1 to 20 of I squared. Now this we could do, right? Got a formula for that one. Minus 6 times the sum of I equals 1 to 20 of I, and we could do that one. Plus, what? 20 times 9, right? Okay, because we can use the formula for that one. That doesn't require further simplification. Okay, so 4 times. Okay, I squared. What's the formula for I squared? And again, n times n. Oh wait, I squared. So it's n times. Okay, what's our n? So we've got 20 times n plus 1 times 21 times 2n plus 1. So that'll be 41 over 6 minus 6 times 20 times, what are we doing? 21. 20 times 21 over 2 plus 180. Okay, so 2 goes into 6 3 times. I got a 20 and a 21. You know what? Maybe we should just leave this as a 20 times 9. Or just get out a calculator, really. But if we leave this, so we'll have a 20 as a common factor here. So we could pull a 20 out, so 25. That, just work it out, just calculate. I'm sure if you had to do it, you could. We get, okay, right. So we got 4 times 20. Okay, 6. What goes into 3, right? 2. So that'll be a 7. 7 times 41. Well, that's doable. That's 287. So this is 287 over 2 minus. We should have left a 2 down there. Put a 2 down there. We could do this with a common denominator of 2, right? Put the 6 back in. This painful process brought to you by lack of calculator. Right? If we used a calculator, just plug it in. You know, we're not going to let you.
Why'd you pull the 4 in front of the entire equation? Shouldn't it be attached to the,
You're right. You are right. Why did I do that? Okay. Good. It's the usual calculus thing. An earlier correction is always better. Yeah, mess that one up. Okay, so, all right, good. Then we can get rid of the 2, right, with the 2. Okay, and then we can get rid of this 2 and put a 3 there. Okay, so now what have we got? We have a common factor of 20. We've got 2 times 287 minus 3 times 21 plus 9. Okay, so we can work this out, right? What's 2 times 287? It's going to end in a 4. And we've got a 1 and 7, 574. Minus 63 plus 9. So 574 minus 63, or let's go 583 minus 63, be like 520, right? Yeah, no, it's 520. Yeah, so 20 times 520, oh wow, it just became easy, right? So you just multiply that by 10, 5,200, and then double it. So 10,400. Oh, and no big panic, my kid's going to be home today to get the watch, so that UPS stuff. Sturm und Drang. She's not flying down to Anaheim until Friday. Actually, for some reason, she's flying to Phoenix and then driving.
Why the hell not?
Might not have been any flights into Anaheim, that's why.
Should we divert orders by hijack?
Yeah, fly us to Anaheim. Okay, infinite series. Now, we can do an infinite series if it's geometric and the common ratio is the absolute value of the common ratio is less than 1. But how can we add an infinite series like this? So we can start off by saying, well, okay, let's take a look. What about n squared? That's really just a constant, right? So let's pull that out. Yeah. So it's 1 over n squared times the sum. Hang on, let's throw the limit on. So the limit as n approaches infinity of 1 over n squared times the sum of I equals 1 to n of just plain old little I. Well, we got a formula for that, right? So it's the limit as n approaches infinity of, let's throw this around. So we got 1 over n squared, and the sum for I equals 1 to n of I is n times n plus 1 over 2, right? n. So what do we want to do with that? Well, we can take an n out from the top and the n squared. So this will be limit as n approaches infinity. So up top we've got n plus 1, and on the bottom we've got 2n. And we know how to show that algebraic, right? We're going to divide through by the highest power of n. So it's the limit as n approaches infinity. So n over n is 1, 1 over n is 1 over n, and 2 over n is 2, right? So divide this by n, this by n, this by n. This is what we get. And now we can do the limit, right? And what do we end up with? 1/2. You knew that just looking at this, right? You just said, oh, forget the 1. But that's how we, the more formal, right, divide by n. So interesting, right? We can add up that infinite series even though but that's infinity squared. All right, let's do the same thing here. So is there a constant here? Yeah, you got a 2, and you got the n cubed, right? So it's going to be 2 over n cubed. So let's be the limit of 2 over n cubed times the sum of I equals 1 to n of I squared. Well, we have an expression for that, right? The expression for the sum of I equals 1 to n of n squared, which is the more complicated one. It's got the 6 in it.
It's actually not complicated. What is the square? How is the square number?
So what do we got here? This is n times n plus 1 times 2n plus 1 over 6. Okay, so before we formalize it, what is it? What is that limit? By inspection, 2/3, right? Because you look at the top, you say, what are we going to end up with? Well, we're going to get an n cubed up top. Or we're going to n cubed on the bottom. Okay, well, but it's not really an n cubed, right? It's really a 2n cubed on the top. You multiply that by 2, get a 4, divided by 6, it's going to be 2/3. So, let's simplify this though, right? So the 2 goes into the 6 3 times. This n takes this to an n squared, and now we can just multiply this out. So the limit as n approaches infinity, so we've got 2n squared plus n plus 2n plus 3n plus 1 over 3n squared. Okay, now it's really obvious that it's 2/3. But we can show it, right? So we're going to divide through by n squared. So we're going to get 2 plus 3 over n plus 1 over n squared over 3. And now we can take the limit. So we're not dividing by 0 anymore, or infinity, and we get 2/3. Is that all there is?
Nothing on the back side.
Yeah.
Oh, thank goodness.
There's doodle sketching stuff.